女士们、先生们，欢迎 Nvidia 创办人暨执行长黄仁勋先生。
Welcome to the stage, Nvidia founder and CEO Jensen Huang.
It's great to be here. My parents are also in the audience. 我爸妈妈来，他们在哪里？ They're up there. Nvidia has been coming to Taiwan for over 30 years. This is the home of many of our treasured partners and dear friends. Over the years, you have seen Nvidia grow up and seen us accomplish many exciting things and have been partnered with me all along the way. Today, we're going to talk about where we are in the industry, where we're going to go, announce some new products, exciting new products and surprising products that open new markets for us, creates new markets, new growth. We're going to talk about great partners and how we're going to develop this ecosystem together. As you know, we are at the epicenter of the computer ecosystem, one of the most important industries of the world. And so it stands to reason when new markets has to be created, we have to create it starting here at the center of the computer ecosystem. And I have some surprises for you, things that you probably wouldn't have guessed. And then, of course, I promise I'll talk about AI. And we'll talk about robotics. The Nvidia story is the reinvention of the computer industry. In fact, the Nvidia story is also the reinvention of our company. As I said, I've been coming here for 30 years. Many of you have been through many of my keynotes. Some of you, all of them. And just as you reflect on the conversation, the things we talked about in the last 30 years, how dramatically changed. We started out as a chip company with a goal of creating a new computing platform. And in 2006, we introduced CUDA, which has revolutionized how computing is done. In 2016, 10 years later, we realized that a new computing approach has arrived. And this new computing approach requires a reinvention of every single layer of the technology stack. The processor is new. The software stack is new. It stands to reason the system is new. And so we invented a new system that on the day I announced it at GTC 2006, no one understood what I was talking about and nobody gave me a PO. That system was called DGX1. DGX1, I donated the first one to a nonprofit company called OpenAI. And it started the AI revolution. Years later, we realized that in fact, this new way of doing software, which is now called artificial intelligence, is unlike traditional ways of running software. Whereas many applications ran on a few processors in a large data center. We call that hyperscale. This new type of application requires many processors working together, serving queries for millions of people. And that data center would be architected fundamentally different. We realized there were two types of networks. One, for north-south, because you still have to control the storage, you still have to have a control plane, you still have to connect to the outside. But the most important network was going to be east-west. The computers talking to each other to try to solve a problem. We recognized the best networking company in east-west traffic for high-performance computing, large-scale distributed processing, a company that was very dear to our company and very close to our heart, a company called Mellanox, and we bought them 5 years ago, 2019. We converted an entire data center into one computing unit. And you heard me say before, the modern computer is an entire data center. The data center is a unit of computing, no longer just a PC, no longer just a server. The entire data center is running one job, and the operating system would change. NVIDIA's data center journey is now very well known. Over the last 3 years, you've seen some of the ideas that we're shaping and how we are starting to see our company differently. No company in history, surely no technology company in history, has ever revealed a roadmap for 5 years at a time. No one would tell you what is coming next. They keep it as a secret, extremely confidential. However, we realized that NVIDIA is not a technology company only anymore. In fact, we're an essential infrastructure company. And how can you plan your infrastructure, your land, your shell, your power, your electricity, all of the necessary financing around all over the world? How would you possibly do that if you didn't understand what I was going to make? And so we described our company's roadmap in fair detail, enough detail that everybody in the world can go off and start building data centers. We realize now we are an AI infrastructure company, an infrastructure company that's essential all around the world. Every region, every industry, every company will build these infrastructures. And what are these infrastructure? These infrastructure, in fact, not unlike the first industrial revolution, when people realized, GE, Westinghouse, Siemens, realized that there was a new type of technology called electricity, and new infrastructure has to be built all around the world. And these infrastructure became essential part of social infrastructure. That infrastructure is now called electricity. Years later, this is during all of our generation, we realized there was a new type of infrastructure. And this new infrastructure was very conceptual, very hard to understand. And this infrastructure called information. This information infrastructure, the first time it was described, made no sense to anybody. But we now realized it is the internet. And every internet is everywhere. And everything is connected to it. Well, there's a new infrastructure now. This new infrastructure is built on top of the first two. And this new infrastructure is an infrastructure of intelligence. I know that right now, when we say there's an intelligence infrastructure, it makes no sense. But I promise you, in 10 years' time, you will look back and you will realize that AI has now integrated into everything. And in fact, we need AI everywhere. And every region, every industry, every country, every company, all needs AI. AI has now part of infrastructure. And this infrastructure, just like the internet, just like electricity, needs factories. And these factories are essentially what we build today. They're not data centers of the past, a $1 trillion industry providing information and storage, supporting all of our ERP systems and our employees. That's a data center of the past. This is similar in the sense that it came from the same industry. It came from all of us, but it's going to emerge as something completely different, completely separated from the world's data center. And these AI data centers, if you will, are improperly described. They are, in fact, AI factories. You apply energy to it, and it produces something incredibly valuable. And these things are called tokens. To the point where companies are starting to talk about how many tokens they produced last quarter and how many tokens they produced last month. Very soon, we'll be talking about how many tokens we produce every hour, just as every single factory does. And so the world has fundamentally changed. We went from a company, on the day that we started our company, I was trying to figure out how big our opportunity was in 1993, and I came to the conclusion NVIDIA's business opportunity was enormous. $300 million. We're going to be rich. $300 million chip industry to a data center opportunity that represents about $1 trillion to now an AI factory, an AI infrastructure industry that will be measured in trillions of dollars. And this is the exciting future that we're undertaking. Now, at its core, everything we do is founded on several important technologies. Of course, I talk about accelerated computing a great deal. I talk about AI a great deal. What makes NVIDIA really special is the fusion of these capabilities. And very especially, the algorithms, the libraries, what we call the CUDA X libraries. We're talking about libraries all the time. And in fact, we're the only technology company in the world that talks about libraries nonstop. And the reason for that is because libraries is at the core of everything that we do. Libraries is what started it all. And I'm going to show you a few new ones today. But before I do that, let me show you a preview of what I'm going to tell you today. Everything you're about to see is simulation, science, and artificial intelligence. Nothing you see here is art. It's all simulation. It just happens to be beautiful. Let's take a look. This is real-time computer graphics I'm standing in front of. This is not a video, this is computer graphics. It's generated by GeForce. This is a brand new GeForce 5060, RTX 5060. And this is from Asus. My good friend Johnny is in the front row. And this is from MSI. And we took this incredible GPU and we shrunk it in here. Does that make any sense? See, this is incredible. And so this is MSI's new laptop with 5060 in it. GeForce brought CUDA to the world. Right now, what you're seeing is every single pixel is ray traced. How is that possible that we're able to simulate photon and deliver this kind of frame rate at this resolution? Well, the reason for that is artificial intelligence. We're only rendering 1 out of 10 pixels. So every pixel that you see, only 1 out of 10 is actually computed. The other 9, AI guessed. Does that make any sense? And it's perfect. It's completely perfect. It guessed it perfectly. Of course, the technology is called DLSS, neural rendering. It took us many, many years to develop. We started developing it the moment we started working on AI, so it's been a 10-year journey. And the advance in computer graphics has been completely revolutionized by AI. GeForce brought AI to the world. Now AI came back and revolutionized GeForce. So really, really amazing. Ladies and gentlemen, GeForce. You know, when you're CEO, you have many children. And GeForce brought us here. And now all of our keynotes is 90% not GeForce. But it's not because we don't love GeForce. GeForce RTX 50 series just had its most successful launch ever, the fastest launch in our history. And PC gaming is now 30 years old. So that tells you something about how incredible GeForce is. Let's talk about libraries. At the core, of course, everything starts with CUDA. And by making CUDA as performant as possible, as pervasive as possible, so that the install base is all over the world, then applications can find a CUDA GPU quite easily. The larger the install base, the more developers want to create libraries. The more libraries, more amazing things are done, better applications, more benefits to users. They buy more computers. The more computers, more CUDA. That feedback path is vitally important. However, accelerated computing is not general purpose computing. General purpose computing writes software, everybody writes it in, Python or C or C++, and you compile it. The methodology for general purpose computing is consistent throughout. Write the application, compile the application, run it on the CPU. However, that fundamentally doesn't work in accelerated computing because if you could do that, it would be called a CPU. What's the point of not just changing the CPU so you could write the software, compile the software, run it on a CPU? The fact that you would have to do something different is actually quite sensible. And the reason for that is because so many people worked on general purpose computing, trillions of dollars of innovation. How is it possible that all of a sudden, a few widgets inside a chip, and all of a sudden computers become 50 times faster, 100 times faster? That makes no sense. And so the logic that we applied is that we could accelerate applications if you understood more about it. You can accelerate applications if you were to create an architecture that are better suited to accelerate, to run at the speed of light, 99% of the runtime, and just even though it's only 5% of the code, which is quite surprising. Most applications, small parts of the code consumes most of the runtime. We made that observation, and so we went after one domain after another. I just showed you computer graphics. We also have numerics. This is CuPy numeric. This is CuPy is the most pervasive numerical library. Arial and Shona. Arial is the world's first GPU accelerated radio signal processing for 5G and 6G. Once we make it software defined, then we can put on top of it AI. So now we could bring AI to 5G and 6G. Parabricks for genomics analysis, Mo9 for medical imaging, Earth-2 for weather prediction, cuQuantum for quantum classical computer architectures and computer systems, CU equivariance and CU tensor, contraction of tensor mathematics, Megatron. This whole row, this whole column here consists of all of our deep learning and all of our libraries necessary for training as well as inference for deep learning. This revolutionized computing. And it all started with all these libraries. Not just CUDA, but cuDNN. On top of cuDNN, there was Megatron, then TensorRT LLM, and then now lately, this brand new operating system for large AI factories, Dynamo. cuDF for data frames like Spark and SQL. Structured data can be accelerated as well. cuML, classical machine learning. Warp, a Pythonic framework for describing CUDA kernels, incredibly successful. cuOpt, mathematical operations, optimizations, things like traveling salesperson, the ability to optimize highly constrained, large number of variables, type of problems like supply chain optimization. This is an incredible success. I'm very excited about cuOpt, cuDSS and cuSparse for sparse structure simulators. Those are used for CAE and CAD, fluid dynamics, finite element analysis, incredibly important for EDAs and CAE industry. And then of course, cuLitho, one of the most important libraries for computational lithography. Mask making could easily take a month. And that mask making process is extremely computationally intensive. And now with cuLitho, we could accelerate that computation by 50 times, 70 times. As a result, this is going to set the stage, open the world for applying AI to lithography in the future. We have great partners here. TSMC is using cuLitho quite extensively. ASML, Synopsys, excellent partners working with us in cuLitho. So the libraries themselves is what makes it possible for us, one domain of application after another domain of science, after another domain of physics, to be able to accelerate those applications. But it also opens up markets for us. We look at particular regions and particular markets and we say, that area could really be important to transform to the new way of doing computing. If general purpose computing, after all these years, has run its course, why hasn't it run its course in every single industry? So one of the most important industries, of course, is telecommunications. Just as the world's cloud data centers have now become software defined, it stands to reason that telecommunication should also be software defined. And so that's the reason why we've taken now some 6 years to refine and optimize a fully accelerated radio access network, RAN stack, that does incredible performance. For data rate per megawatt, or data rate per watt, we are now on par with the state-of-the-art ASICs. And so once we could do that, once we could achieve that level of performance and functionality, then after that we can layer on top AI. And so we have great partners here. You could see SoftBank and T-Mobile, Indosat and Vodafone are doing trials. Nokia, Samsung, Kyocera are working with us on the full stack. Fujitsu and Cisco are working on the systems. And so now we have the ability to introduce the idea of AI on 5G or AI on 6G along with AI on computing. We're doing that with quantum computing. Quantum computing is still at the noisy intermediate scale quantum called NISQ. However, there are many, many good applications we could already start to do. And so we're excited about that. We're working on a quantum classical or quantum GPU computing platform. We call it CUDA-Q, working with amazing companies around the world. GPUs could be used for pre-processing and post-processing, for error correction, for control. And so in the future, I predict that all supercomputers will have quantum accelerators, all have quantum QPUs connected to it. And so a supercomputer would be a QPU with QPUs and GPUs and some CPUs. And that would be the representation of a modern computer. So working with a lot of great companies in this area. AI. 12 years ago, we started with perception. AI models that can understand patterns, recognize speech, recognize images. That was the beginning. The last 5 years, we've been talking about generative AI, the ability for AI to not just understand, but to generate. And so it could generate from text to text. We use that all the time in ChatGPT. Text to images, text to video, video to text, images to text. Almost anything to anything. which is the really amazing thing about AI, that we've discovered a universal function approximator, a universal translator. It can translate from anything to anything else if we can simply tokenize it, represent the bits of information. Well, now we have reached a level of AI that's really important. Generative AI gave us one-shot AI. You give it text and it gives you text back. That was 2 years ago when we first engaged ChatGPT. That was the big, amazing breakthrough. You give it text and it gives you text back. It predicts the next word, predicts the next paragraph. However, intelligence is much more than just what you've learned from a lot of data that you've studied. Intelligence includes the ability to reason, to be able to solve problems that you've not seen before, to break it down step by step, to maybe apply some rules and theorems to solve a problem you've never seen, to be able to simulate multiple options and weigh its benefits. Some of the technology you might have heard about, chain of thought, breaking it down step by step, tree of thought, coming up with a whole bunch of paths. All of these technologies are leading the ability for AI to be able to reason. Now, the amazing thing is, once you have the ability to reason, and you have the ability to perceive, that is, let's say, multimodal read PDFs, you could do search, you can use tools, you have now agentic AI. This agentic AI just does something that I've just described all of us do. We're given a goal, we break it down step by step, we reason about what to do, what's the best way to do it, we consider its consequences, and then we start executing the plan. The plan might include doing some research, might include doing some work, using some tools. It might include reaching out to another AI agent to collaborate with it. Agentic AI is basically understand, think, and act. Well, understand, think, and act is the robotics loop. Agentic AI is basically a robot in a digital form. These are going to be really important in the coming years. We're seeing enormous progress in this area. The next wave, beyond that, is physical AI. AI that understands the world. They understand things like inertia, friction, cause and effect. That if I roll a ball and it goes under a car, depending on the speed of the ball, it probably went to the other side of the car, but the ball did not disappear. Object permanence. You might be able to reason that if there's a table in front of you and you have to go to the other side, the best way to do it is not to go right through it. The best way is maybe go around it or underneath it. To be able to reason about these physical things is really essential to the next era of AI. We call that physical AI. And so in this particular case, you're seeing us simply prompt the AI and it generates videos to train a self-driving car in different scenarios, and I'll show you more of that later. That's a dog. It said, generate me a dog, generate me one with a bird, with people. And it started out with the image on the left. And then the phase after that, we take reasoning systems, generative systems, physical AI, and this level of capability would now go into a physical embodiment. We call it a robot. If you could imagine that you can prompt an AI to generate a video to reach and pick up a bottle, of course you could imagine telling a robot to reach out and pick up the bottle. The AI capability today has the ability to do those things. Well, the computer that's where we're going in the near future. The computer that we're building to make this possible has properties that are very different than the previous. The revolutionary computer called Hopper came into the world about 3 years ago, and it revolutionized AI as we know it. It became probably the most popular, most well-known computer in the world. In the last several years, we've been working on a new computer to make it possible for us to do inference time scaling, or basically thinking incredibly fast. Because when you think, you're generating a lot of tokens in your head, if you will. You're generating a lot of thoughts, and you iterate in your brain before you produce the answer. So what used to be one-shot AI is now going to be thinking AI, reasoning AI, inference time scaling AI. And that's going to take a lot more computation. And so we created a new system called Grace Blackwell. Grace Blackwell does several things. It has the ability to scale up. Scale up means to turn what is a computer into a giant computer. Scale out is to take a computer and connect many of them together and let the work be done in many different computers. Scaling out is easy. Scaling up is incredibly hard. Building larger computers that is beyond the limits of semiconductor physics is insanely hard. And that's what Grace Blackwell does. Grace Blackwell broke just about everything. And all of you in the audience, many of you are partnering with us to build Grace Blackwell systems. I'm so happy to say that we're in full production, but we can also say it was incredibly challenging. Although the Blackwell systems based on HGX has been in full production since the end of last year and has been available since February, we are now just putting online all the Grace Blackwell systems. They're coming online all over the place every single day. It's available in CoreWeave now for several weeks. It's already being used by many CSPs. And now you're starting to see it coming up from everywhere. Everybody's starting to tweet out that Grace Blackwell is in full production. In Q3 of this year, just as I promised, every single year, we will increase the performance of our platform every single year like rhythm. And this year, in Q3, we'll upgrade to Grace Blackwell GB300. The GB300 will increase the same architecture, same physical footprint, same electrical and mechanicals, but the chips inside have been upgraded. It has upgraded with a new Blackwell chip. It's now 1.5 times more inference performance, has 1.5 times more HBM memory, and it has 2 times more networking. And so the overall system performance is higher. Well, let's take a look at what's inside Grace Blackwell. Grace Blackwell starts with this compute node. This compute node right here, this is one of the compute nodes. This is what the last generation looks like, the B200. This is what B300 looks like. Notice right here in the center, it's 100% liquid cooled now, but otherwise, externally, it's the same. You could plug it into the same systems and same chassis. And so this is the Grace Blackwell GB300 system. It's 1.5 times more inference performance. The training performance is about the same, but the inference performance is 1.5 times more. Now this particular system here is 40 petaflops, which is approximately the performance of the Sierra supercomputer in 2018. The Sierra supercomputer has 18,000 GPUs, Volta GPUs. This one node here replaces that entire supercomputer. 4,000 times increase in performance in 6 years. That is extreme Moore's law. Remember, I've said before that Nvidia has been scaling computing by about 1 million times every 10 years. And we're still on that track. But the way to do that is not just to make the chips faster. There's only a limit to how fast you can make chips and how big you can make chips. In the case of Blackwell, we even connected 2 chips together to make it possible. TSMC worked with us to invent a new CoWoS process called CoWoS-L that made it possible for us to create these giant chips. But still, we want chips way bigger than that. And so we had to create what is called NVLink. This is the world's fastest switch. This NVLink here, right here, is 7.2 terabytes per second. 9 of these go into that rack. And those 9 switches are connected by this miracle. This is quite heavy. That's because I'm quite strong. I made it look so light, but this is 70 pounds. And so this is the NVLink spine. 2 miles of cables, 5,000 cables structured, all coaxed, impedance matched, and it connects all 72 GPUs to all of the other 72 GPUs across this network called NVLink switch. 130 terabytes per second of bandwidth across the NVLink spine. So just put in perspective, the peak traffic of the entire internet, is 900 terabits per second. Divide that by 8. This moves more traffic than the entire internet. One NVLink spine across this 9 of these NVLink switches, so that every single GPU can talk to every other GPU at exactly the same time. This is the miracle of GB200. And because there's a limit to how far you can drive SerDes, this is as far as any SerDes has ever driven. From chip, this goes chip to the switch, out to the spine, to any other switch, any other chip, all electrical. And so that limit caused us to put everything in one rack. And that one rack is 120 kilowatts, which is the reason why everything has to be liquid cooled. We now have the ability to disaggregate the GPUs out of one motherboard, essentially, across an entire rack. And so that entire rack is one motherboard. That's the miracle. Completely disaggregated, and now the GPU performance is incredible, the amount of memory is incredible, the networking bandwidth is incredible, and now we can really scale these out. Once we scale it up, then we can scale it out into large systems. And notice almost everything NVIDIA builds are gigantic. And the reason for that is because we're not building data centers and servers, we're building AI factories. This is CoreWeave, this is Oracle Cloud. The power density of each rack is so great. They have to put them further apart so that the power density could be distributed. But really, in the end, we're not building data centers, we're building AI factories. And this is the XAI Colossus factory. This is Stargate, 4 million square feet, 4 million square feet, 1 gigawatt. And so just think about this factory here. This 1 gigawatt factory is probably going to be about, 60 to 80 billion dollars. Out of that 60 to 80 billion dollars, the electronics, the computing part of it, these systems are 40, 50 billion dollars of it. And so these are gigantic factory investments. The reason why people build factories is because you know the answer. The more you buy, say it with me. The more you buy, the more you make. That's what factories do. Okay. The technology is so complicated. And in fact, just looking at it here, you still cannot get the deep appreciation of the amazing work that's being done in all of our partners and all of the companies here in the audience in Taiwan. And so we made you a movie. I made you a movie. Take a look.
Blackwell is an engineering marvel. It begins as a blank silicon wafer at TSMC. Hundreds of chip processing and ultraviolet lithography steps build up each of the 200 billion transistors, layer by layer, on a 12-inch wafer. The wafer is scribed into individual Blackwell die, tested and sorted, separating the good dies to move forward. The chip-on-wafer on substrate process, done at TSMC, SPIL, and Amkor, attaches 32 Blackwell dies and 128 HBM stacks on a custom silicon interposer wafer. Metal interconnect traces are etched directly into it, connecting Blackwell GPUs and HBM stacks into each system and package unit, locking everything into place. Then the assembly is baked, molded, and cured, creating the Blackwell B200 superchip. At KYEC, each Blackwell is stress-tested in ovens at 125 degrees Celsius and pushed to its limits for several hours. Back at Foxconn, robots work around the clock to pick and place over 10,000 components onto the Grace Blackwell PCB. Meanwhile, additional components are being prepared at factories across the globe. Custom liquid cooling copper blocks from Cooler Master, AVC, Aorus, and Delta keep the chips at optimal temperatures. At another Foxconn facility, ConnectX-7 SuperNICs are built to enable scale-out communications, and Bluefield 3 DPUs to offload and accelerate networking, storage, and security tasks. All these parts converge to be carefully integrated into GB200 compute trays. NVLink is the breakthrough high-speed link that Nvidia invented to connect multiple GPUs and scale up into a massive virtual GPU. The NVLink switch tray is constructed with NVLink switch chips, providing 14.4 terabytes per second of all-to-all bandwidth. NVLink spines form a custom blind-mated backplane, integrating 5,000 copper cables to deliver 130 terabytes per second of all-to-all bandwidth. This connects all 72 Blackwells, or 144 GPU dies, into one giant GPU. From around the world, parts arrive. From Foxconn, Wistron, Quanta, Dell, Asus, Gigabyte, HPE, Supermicro, and other partners to be assembled by skilled technicians into a rack-scale AI supercomputer. In total, 1.2 million components, 2 miles of copper cable, 130 trillion transistors, weighing 1,800 kilograms. From the first transistor etched into a wafer to the last bolt fastening the Blackwell rack, every step carries the weight of our partners' dedication, precision, and craft. Blackwell is more than a technological wonder. It's a testament to the marvel of the Taiwan technology ecosystem. We couldn't be prouder of what we've achieved together. Thank you, Taiwan.
Thank you. Thank you. That was pretty incredible, right? But that was you. That was you. Thank you. Well, Taiwan doesn't just build supercomputers for the world. Today, I'm very happy to announce that we're also building AI for Taiwan. And so today we're announcing that Foxconn, Taiwan, the Taiwanese government, Nvidia, TSMC, we're going to build the first giant AI supercomputer here for the AI infrastructure and the AI ecosystem of Taiwan. Thank you. Is there anybody who needs an AI computer? Any AI researchers in the audience? Every single student, every researcher, every scientist, every startup, every large established company, TSMC themselves does enormous amounts of AI and scientific research already. And so Foxconn does an enormous amount of work in robotics. I know that there are many other companies in the audience, I'm going to mention you in just a second, that are doing robotics research and AI research. And so having a world-class AI infrastructure here in Taiwan is really important. All of that is so that we could build a very large chip. And NVLink and Blackwell, this generation, made it possible for us to create these incredible systems. Here's one from Pegatron and QCT and Wistron and WeWin. This is from Foxconn and Gigabyte and Asus. And you can see the front and the back of it. And its entire goal is to take these Blackwell chips that are, you could see how big they are, and turn it into one massive chip. Now, the ability to do that, of course, was made possible by NVLink. But it understates the complexity of the system architecture, the rich software ecosystem that connects it all together, the entire ecosystem of 150 companies that came together to build this. This architecture and the entire ecosystem in technology, in software, in industry has been the work of 3 years. This is a massive industrial investment. And now, we would like to make it possible for anybody who wants to build data centers. It could be a whole bunch of Nvidia GB200s or 300s and accelerated computing systems from Nvidia. It could be somebody else. And so today, we're announcing something very special. We're announcing Nvidia NVLink Fusion. NVLink Fusion is so that you can build semi-custom AI infrastructure. We'll be ready, will be available shortly, probably in a few weeks. We have tremendous partners working with us. Dell, HPI, Asus, MSI, Gigabyte, Lenovo. Incredible partners working with us. And this is the DGX Spark. This is actually a production unit. This is our version. This is our version. However, our partners are building a whole bunch of different versions. This is designed for AI native developers. If you're a developer, you're a student, you're a researcher, and you don't want to keep opening up the cloud and getting it prepared, and then when you're done scrubbing it, okay? But you would just like to have your own, basically your own AI cloud sitting right next to you, and it's always on, always waiting for you. It allows you to do your prototyping, early development, and this is what's amazing. This is DGX Spark. It's 1 petaflops and 128 gigabytes. In 2016, when I delivered DGX1, this is just the bezel. I can't lift the whole computer. It's 300 pounds. This is DGX1. This is 1 petaflops and 128 gigabytes. Of course, this is 128 gigabytes of HBM memory, and this is 128 gigabytes of LPDDR5X. The performance is in fact quite similar. But what's most important is that the work that you could work on this is the same work you could do here. It's an incredible achievement over just the course of about 10 years. Okay, so this is DGX Spark for anybody who would like to have their own AI supercomputer. And it's, I'll let all of our partners price it for themselves, but one thing for sure, everybody can have one for Christmas. Okay, I've got another computer I want to show you. If that's not enough, and you would still like to have your own personal, thank you, Janine. This is Janine Paul, ladies and gentlemen. If that one isn't big enough for you, here's one. This is another desk side. This is also going to be available from Dell and HPI, Asus, Gigabyte, MSI, Lenovo. It'll be available from Box, from Lambda, amazing workstation companies. And this is going to be your own personal DGX supercomputer. This computer is the most performance you can possibly get out of a wall socket. You could put this in your kitchen, but just barely. If you put this in your kitchen and then somebody runs the microwave, I think that's the limit. And so this is the limit. This is the limit of what you can get out of a wall outlet. And this is a DGX station. The programming model of this and the giant systems that I showed you are the same. That's the amazing thing. One architecture, and this has the ability, enough capacity and performance to run a 1 trillion parameter AI model. Remember, Llama is Llama 70B. A 1 trillion parameter model is going to run wonderfully on this machine. Okay, so that's the DGX station. So now let's talk about, remember these systems are, thank you, Janine. These systems are AI natives. They're AI native computers. They're computers built for this new generation of software. It doesn't have to be x86 compatible. It doesn't have to run traditional IT software. It doesn't have to run hypervisors. It doesn't have to run it doesn't have to run Windows. These computers are designed for the modern AI native applications. Of course, these AI applications could be APIs that can be called upon by the traditional and the classical applications. But in order for us to bring AI into a new world, and this new world is enterprise IT, we have to go back to our roots, and we have to reinvent computing and bring AI into traditional enterprise computing. Now, enterprise computing, as we know, is really 3 layers. It's not just the computing layer. It's compute, storage, and networking. It's always compute, storage, and networking. And just as AI has changed everything, it stands to reason that AI must have changed compute, storage, and networking for enterprise IT as well. Well, that lower layer has to be completely reinvented, and we're in the process of doing that. I'm going to show you some new products that opens up, unlocks enterprise IT for us. It has to work with the traditional IT industry, and it has to add a new capability. And the new capability for enterprise is agentic AI. Basically, digital marketing campaign manager, a digital researcher, a digital software engineer, digital customer service, digital chip designer, digital supply chain manager, digital versions, AI versions of all of the work that we used to do. And as I mentioned earlier, agentic AI has the ability to reason, use tools, work with other AIs. So in a lot of ways, these are digital workers. They're digital employees. The world has a shortage of labor. We have a shortage of workers. By 2030, by about 30 to 50 million shortage. It's actually limiting the world's ability to grow. And so now we have these digital agents that can work with us. 100% of NVIDIA software engineers now have digital agents working with them so that they can help them, assist them in developing better code and more productively. And so in the future, you're going to have this layer, that's our vision. You're going to have a layer of agentic AIs, AI agents. And so what's going to happen to the world? What's going to happen to enterprise? Whereas we have HR for human workers, we're going to have IT becoming the HR of digital workers. And so we have to create the necessary tools for today's IT industry, today's IT workers, to be able to manage, improve, evaluate a whole family of AI agents that are working inside their company. And so that's the vision of what we want to build. But first, we have to reinvent computing. Remember what I said. Enterprise IT works on x86. It runs traditional software, such as hypervisors from VMware or IBM Red Hat or Nutanix. It runs a whole bunch of classical applications. And we need to have computers that do the same thing while it adds this new capability, called Agent AI. And so let's take a look at that. Okay, this is the brand new RTX Pro Enterprise and Omniverse server. This server can run everything. It has x86, of course. It can run all of the classical hypervisors. It runs Kubernetes in those hypervisors. So the way that your IT department wants to manage your network and how they want to manage your clusters and orchestrate workload works exactly the same way. It has the ability to even stream Citrix and what other virtual desktops to your PC. Everything that runs in the world today should run here. Omniverse runs on here perfectly. But in addition to that, this is the computer for enterprise AI agents. Those AI agents could be only text. Those AI agents could also be computer graphics. Little TJs, coming to you, little toy Jensens coming to see you, helping you do work. And so those AI agents My entire keynote is your work. It's so excellent. Well, it stands to reason that Taiwan, at the center of the most advanced industry, the epicenter where AI and robotics is going to come from, it stands to reason that this is an extraordinary opportunity for Taiwan. This is also the largest electronics manufacturing region in the world. And so it stands to reason that AI and robotics will transform everything that we do. And so it's really quite extraordinary that for one of the first times in history that the work you do has revolutionized every industry, and now it's going to come back to revolutionize yours. At the beginning, I said that GeForce brought AI to the world. And then AI came back and transformed GeForce. You brought AI to the world. AI will now come back and transform everything that you do. It's been a great pleasure working with all of you. Thank you. I have a new product. I announced several products already today, but I have a new product to announce. We've been building out in Space Dock for some time. And I think it's time for us to reveal one of the largest products that we've ever built. And it's parked outside waiting for us. Let's see how it goes. Nvidia Constellation. Nvidia Constellation. Well, as you know, we have been growing. And all of our partnerships with you have been growing. The number of engineers we have here in Taiwan have been growing. And so we are growing beyond the limits of our current office. And so I'm going to build them a brand new NVIDIA Taiwan office, and it's called NVIDIA Constellation. We've also been selecting the sites. And all of the mayors and all the different cities have been very kind to us. And I think we got some nice deals. I'm not sure. It seems quite expensive. But prime real estate is prime real estate. And so today, I'm very pleased to announce that NVIDIA Constellation will be at Beitou Shiling. We have negotiated the transfer of the lease from the current owners of that lease. However, I understand that in order for the mayor to approve that lease, he wanted to know whether the people of Taipei approve of us building a large, beautiful NVIDIA Constellation here. Do you? He also asked for you to call him. And so I'm sure you know his numbers. Everybody call him right away. Tell him that you think it's a great idea. So this is going to be NVIDIA Constellation. We're going to build it. We're going to start building as soon as we can. We need the office space. NVIDIA Constellation, Beidou, Xiling. Very exciting. Okay. Well, I want to thank all of you. I want to thank all of you for your partnership over the years. We are at a once-in-a-lifetime opportunity. It is not an understatement to say that the opportunity ahead of us is extraordinary. For the very first time in all of our time together, not only are we creating the next generation of IT, we've done that several times. From PC to internet, to cloud, to mobile cloud, we've done that several times. But this time, not only are we creating the next generation of IT, we are in fact creating a whole new industry. This whole new industry is going to expose us to giant opportunities ahead. I look forward to partnering with all of you on building AI factories, agents for enterprises, robots, all of you amazing partners building the ecosystem with us around one architecture. And so I want to thank all of you for coming today. Have a great Computex, everybody. 大家谢谢. Thank you. Thank you for coming. Thank you.